3.5 billion years ago, Mars had rivers. It had lakes. Some evidence points to entire oceans, covering a fraction of its northern hemisphere, under skies wrapped in an atmosphere thick enough to keep liquid water stable on the surface. Today, Mars is a frozen, rust-colored desert with an atmosphere so thin that liquid water boils away almost instantly if it ever reaches the surface. Something happened to Mars. Something took an Earth-like world and turned it into what we see today. For the better part of a decade, NASA had a spacecraft in orbit whose entire job was answering that exact question. That spacecraft, called MAVEN, just went silent for good in 2026, and its final, complete body of work has done something rare in planetary science. It's confirmed the mechanism that killed Mars, while also revealing that the popular version of this story, the one you've probably already heard, is only about half right. Here's what actually happened to Mars, what NASA's now-retired spacecraft proved beyond reasonable doubt, and what an entirely different set of scientists discovered at almost exactly the same time. A discovery that changes where we should be looking if we ever want to find what Mars lost. I'm Jameson Evans, and this is the story of the planet next door, what killed it, and where the evidence has been hiding the whole time. Subscribe now, because the ending of this story is not what you'd expect. To understand what killed Mars, you first need to understand what Mars had to lose. Roughly 4 billion years ago, Mars and Earth started out in surprisingly similar positions. Both were rocky planets with active interiors, both likely had reasonably thick atmospheres rich in carbon dioxide, and both show geological evidence of liquid water on their surfaces, river channels, lake beds, and mineral deposits that, on Earth, only form in the presence of water. NASA's Opportunity rover found small mineral spherules made of hematite on the Martian surface, a mineral that requires liquid water to form, confirming water once genuinely flowed there. But Mars had two structural disadvantages Earth didn't. First, it's smaller, roughly half Earth's diameter, which means its interior cooled faster. Somewhere around 4 billion years ago, the molten iron core that generates a planet's magnetic field through internal convection largely shut down on Mars. Earth's equivalent dynamo is still running today, generating the magnetic field that deflects the solar wind around our entire planet like an invisible force field. Mars lost that shield almost entirely, left with only weak, patchy pockets of magnetism frozen into certain regions of its crust, the fossil remnant of a field that no longer actively protects the planet. Second, Mars has no active plate tectonics. On Earth, shifting continental plates constantly recycle rock, dragging carbon-absorbing minerals down into the mantle and releasing fresh carbon dioxide back into the atmosphere through volcanic activity, a slow, planet-scale thermostat that keeps our atmosphere replenished over geological time. Mars, without that recycling system, has no equivalent way to top up whatever it loses. Put those two things together, no protective magnetic field, no way to replenish lost gas, and you have a planet that was structurally set up, from very early in its history, to slowly lose whatever atmosphere it started with. The question that took decades to answer wasn't whether Mars lost its atmosphere. Geologists had already established that much from the surface evidence. The question was exactly how, and exactly where all of it actually went. That's the question NASA built the MAVEN spacecraft to answer. MAVEN, short for Mars Atmosphere and Volatile Evolution, launched in 2013 and arrived at Mars in September 2014, carrying instruments specifically designed to measure how gas was escaping the top of the Martian atmosphere in real time, rather than just studying the geological aftermath on the ground. What MAVEN found over its first several years in orbit became one of the defining results in modern planetary science. Because Mars has essentially no global magnetic field, the solar wind, the constant stream of charged particles blowing outward from the sun, doesn't get deflected around the planet the way it does at Earth. Instead, it slams directly into the upper Martian atmosphere. MAVEN measured this happening in real time. Charged particles from the solar wind picking up neutral gas molecules at the top of the atmosphere and physically knocking them out into space, a process called sputtering. Mission scientists calculated that the sun was stripping away roughly 100 grams of atmospheric gas every single second, and during major solar storms, that rate jumped by 10 to 20 times or more. MAVEN also found a second, elegant line of evidence confirming this had been going on for billions of years. Different isotopes of the same element, heavier and lighter versions of atoms like argon, escape into space at different rates, with lighter isotopes drifting away more easily. By carefully measuring the ratio of heavy to light argon isotopes in today's thin Martian atmosphere, and comparing it to the ratio you'd expect in a planet's primordial atmosphere, the MAVEN team calculated that Mars had lost roughly 65% of the argon it ever had, and using the same method, they concluded the majority of the planet's original carbon dioxide had likely been lost the same way, through this same sputtering process, over billions of years. This became the story that made headlines for the better part of a decade. The sun killed Mars. No magnetic shield, no protection, and a slow, billion-year bombardment by the solar wind that ground the planet's atmosphere down to almost nothing. The twist nobody saw coming. Here's where the story gets genuinely more interesting, and where two completely separate teams of scientists, working on totally different projects using totally different instruments, stumbled into the same uncomfortable realization at almost exactly the same time in 2024. When researchers tried to run detailed climate simulations using atmospheric escape as the sole mechanism, plugging in MAVEN's measured stripping rates and extrapolating them across Mars's entire history, the numbers didn't fully add up. Escape to space could account for a meaningful fraction of the missing water and gas, but not all of it. And it particularly struggled to explain just how much carbon had vanished. If all three rocky inner planets started with roughly similar primordial atmospheres, Mars appears to have lost at least 90% of its original carbon, and sputtering alone, even running continuously for billions of years, couldn't plausibly account for a loss that large. So where did the rest of it go? In August 2024, a team of geophysicists analyzing years of data from NASA's InSight lander, which spent 4 years listening to the extremely faint seismic vibrations of Mars quakes traveling through the planet's interior, announced they'd found a giant reservoir of liquid water, not lost to space at all, but sitting deep underground. Seismic waves change subtly depending on the density and structure of whatever rock they pass through, and by analyzing those changes, the team calculated there's enough liquid water trapped between cracks and pores in Martian rock, roughly 7 to 13 miles below the surface, to cover the entire planet in a layer 1 to 2 kilometers deep. Geophysicist Michael Manga, who worked on the study, noted that finding a reservoir like that opens a real window into what Mars's ancient climate could have supported. Only a month later, an entirely separate team working at MIT announced they might have found where a huge fraction of the missing carbon dioxide had gone, and they found it almost by accident while studying an entirely different problem here on Earth. The team had been researching a type of clay mineral called smectite, which has a microscopic, accordion-like folded structure capable of trapping and holding on to carbon dioxide and methane for billions of years. One researcher on the team happened to notice that Martian surface maps show smectite clay covering large portions of the planet, and started wondering whether that same trapping process could account for Mars's vanished atmosphere. The mechanism they worked out: water seeping through Mars's iron-rich volcanic crust reacts chemically with a mineral called olivine, releasing hydrogen and rusting the iron in the process, which is part of why Mars is red. That released hydrogen bonds with dissolved carbon dioxide to form methane, and over time, the reaction transforms the original rock into smectite clay that then physically traps that methane inside its folded structure. Running the numbers, the team calculated that if Mars's crust holds roughly a kilometer of the smectite clay, it could be sequestering somewhere around 80% of the planet's entire missing atmospheric carbon dioxide. As lead researcher Joshua Murray put it, Mars's missing atmosphere might be hiding in plain sight. Neither of these two discoveries erased or contradicted what MAVEN had found. The solar wind absolutely has been stripping Mars's atmosphere into space for billions of years, exactly as measured. But it turns out that mechanism was never the whole story. It was one half of a two-part disappearing act, with the other half happening quietly, underground, the entire time. This is where the story catches up to right now, in 2026. On December 6, 2025, NASA unexpectedly lost contact with MAVEN when the spacecraft swung behind Mars during a routine orbit and simply didn't reappear on schedule. After months of investigation by an anomaly review board, NASA confirmed on June 3, 2026, that the spacecraft was in an unrecoverable state, likely the result of excessive, uncontrolled spinning that drained its batteries faster than they could recharge. After 11 years in orbit, the mission that had spent over a decade directly measuring how the sun was stripping Mars's atmosphere was declared officially over. In the mission's closing statements, MAVEN's principal investigator, Shannon Curry, reflecting on more than a decade of results, said the team was exceptionally proud of everything the mission had discovered. And what the mission leaves behind, taken together with the newer underground discoveries from 2024, is arguably a more complete and more useful answer than either finding could have provided alone. Mars wasn't killed by one single process. It was killed by two processes running at the same time, for billions of years, the sun steadily blasting a fraction of its atmosphere into space from above, while separately chemistry was quietly locking a huge share of the rest away into the crust below, where it has been sitting, essentially untouched, ever since. That distinction isn't just academically interesting, it has real, practical consequences for future Mars exploration. If a large fraction of the planet's original water and carbon genuinely never left Mars at all, that changes what future missions might realistically be looking for. The underground water Maven's own instruments couldn't directly detect, sitting 11 to 20 kilometers down, is too deep to reasonably extract with current technology, but it represents a real target for future geological and potentially astrobiological study, since environments like that can, in principle, support microbial life the way deep mines and ocean floor environments do on Earth. The methane trapped in surface and near-surface clay deposits sits much closer to the surface, and could plausibly be extracted by future missions as an actual practical resource for scientific study, or even, eventually, as fuel. There's also a broader lesson here for how scientists study other planets, including ones we've never visited. Mars is, in effect, a natural experiment showing what happens to an Earth-like planet that loses its magnetic shield. Atmosphere and water don't just vanish, they migrate, some to space and apparently a great deal more into the ground. That combined picture is now part of how researchers model atmospheric survival on rocky exoplanets discovered around other stars, when trying to judge which ones might actually be capable of holding onto enough atmosphere and water to be considered habitable. There's something worth sitting with in how this story actually resolved. For years, the version of events that made headlines was simple, dramatic, and a little bit frightening. The sun killed Mars, stripping it bare over billions of years while it sat defenseless without a magnetic field. That story was true. It just wasn't complete. The fuller picture, pieced together only recently from a spacecraft listening to Marsquakes and a team of geologists studying clay minerals for an entirely unrelated reason, is quieter and in some ways stranger. Much of what people assumed was blasted into the vacuum of space never actually left the planet at all. It's still there, sitting in cracks in the rock miles beneath the rust-colored surface, and folded into clay minerals closer to the top, waiting, essentially undisturbed, for billions of years. Maven spent 11 years staring outward and upward, watching atmosphere get stripped away particle by particle, and in doing so helped confirm one real half of what killed Mars. It took a seismometer listening downward, and a team of geologists who weren't even thinking about Mars when they started, to find the other half hiding directly beneath the surface the whole time. Sometimes the full answer to what happened to a planet isn't found by watching where things go. It's found by finally thinking to look at where they might have stayed. If you want to understand what future missions might find when they finally go looking for what's buried under the Martian surface, subscribe and turn on notifications. Drop a comment with which half of this story surprised you more, the sun or the rock, and share this with someone who'd want to know that Mars's missing atmosphere might not be missing at all.